Dear friends, hi. I'm really happy to introduce to you our new lecturers, Shamil Asghari, who is from Santa Clara University, but actually he received his PhD from Brown University, which is also in the United States. And it was happened in 2019. Then he has a postdoctoral position at the University of British Columbia, which is in Canada. And last year, he joined to Santa Clara University. Now he is also joined to us, and he's going to give a mini course on Paley graphs and theory of directions. So during this mini course, 3 lectures will be issued, and the first one is about introduction to Paley graphs. So, Tommy, the floor is yours.
Thank you very much, Elena, for a very nice introduction, and also for the invitation to talk about Paley graphs. I will mostly talk about what I have learned from my collaborators, from the literature about Paley graphs. So in particular, nothing in this lecture will be my results, but these are the results that I really appreciate, and I wanted to share it with you. And there's a lot of history behind Paley graphs, as we're going to see, but I will also talk about a few of the very recent results that was proved this year. Not only this year, I will even mention a result that was proved last month, so a month ago in September, that is related to Paley graphs. Okay, so let's go ahead and get started. And we're going to start by defining Paley graphs. Let Q be an odd prime power such that Q is equal to 1 modulo 4. And as usual, FQ is going to denote the finite field of order Q. Then we define the Paley graph PQ, which will have Q elements, and it's defined as follows. So Paley graph of order Q is the graph whose vertices are the elements of the finite field FQ. And we write a plus here just to emphasize that we are viewing FQ as a abelian group under addition. So those are the vertices. The vertices are elements of your finite field. So now I have to tell you what the edges are. And the edges are determined as follows. There's an edge between x and y if x minus y is a perfect square. The Paley graph is also denoted by PQ in some references. Let me mention that Paley graph is an instance of what's known as a Cayley graph. So in particular, Paley graph is the Cayley graph whose underlying abelian group is the additive group of a finite field. And there should be a square here, and the connection set is the set of squares in FQ. So there should be a little square here at the top. So more generally, if G is an abelian group and S is a set with S equals to minus S, then the Cayley graph is defined as follows. The vertex set of X is G, namely the elements of the abelian group, and the 2 vertices are connected by an edge if and only if the difference between them lies in S, the connection set. So in the case of the Paley graph, the group G is the abelian group, which is the additive group of a finite field, and the set S, it's the set of squares. This is the set S, the set of squares in a finite field. And here is a picture of one of the Paley graphs. So this picture is the Paley graph of order 13. Now, what that means is that the elements of the vertices are the elements of finite field of order 13. And because 13 is prime, finite field of order 13 is simply the numbers from 0 up to 12 with modular arithmetic, mod 13 as the addition and multiplication operations. And in this picture, vertex labeled I just represents the class of I mod 13. And here we see that, for example, 1 is connected to 5. That's because the difference between them is a square mod 13. So 5 minus 1 is 4, which is a square mod 14. And you can see other ones too. For example, 1 is connected to 10 because 10 minus 1 is 9, which is a square mod 13. So as you can see from the picture, it's a highly symmetric and quite an elegant graph. And this is only the Paley graph of order 13. So Paley graph is an example of strongly regular graph. So let me remind you what that means. Strongly regular graph is a stronger notion than just being regular. So a k-regular graph is a graph where every vertex has k neighbors. But a strongly regular graph is a stronger notion. So here's how it's defined. If y is a k-regular graph with n vertices, such that any two adjacent vertices have lambda common neighbors, and any two non-adjacent vertices have mu common neighbors, then we say that y is a strongly regular graph with parameters nk lambda mu. So we can see how this kind of indicates that there's even more symmetry in the graph. I mean, the way we think about regular graphs is that every vertex has same degree. So there's some sort of symmetry in the graph, at least as far as the number of neighbors concerned. But this is indicating that there's further symmetry somehow, that not only every vertex have the same number of neighbors, but in fact, any two adjacent vertices have same number of common neighbors, and any two non-adjacent vertices has another fixed number of common neighbors. And strongly regular graphs is one of the widely studied, intensely studied subfields in the field of algebraic graph theory. And Paley graphs happen to be one of them. In particular, here's the result. If Q is equal to 1 modulo 4, the Paley graph is strongly regular graph with the following parameters. So Q, remember, is the number of vertices in the graph. And then Q minus 1 over 2 is the K here, which is the K regular graph part. So this is the vertex degree for every vertex. So every element has exactly Q minus 1 over 2 neighbors in the Paley graph. And this is kind of evident because let's look at, for example, 0. How many neighbors does 0 have? Well, to be a neighbor of 0, it means the difference between the element and 0 must be a square in a finite field. But we know that the non-zero squares come in half. So out of Q minus 1 elements, exactly half of them are squares and half of them are non-squares. So that's why, for example, 0, the element 0 has exactly Q minus 1 over 2 neighbors. But the same argument really works for any other vertex. So this is a Q minus 1 over 2 regular graph, and it takes a bit more computation to understand that that any two neighbors in the Paley graph, in fact, share Q minus 5 over 4 neighbors, common neighbors, and any non-adjacent vertices also share Q minus 1 over 4 common neighbors. And it's also a standard fact that if you have a strongly regular graph, then the eigenvalues of the graph is very constricted. In fact, a strongly regular graph can only have 3 eigenvalues. And you can calculate that the eigenvalues of the Paley graph are Q minus 1 over 2 with multiplicity 1, and 1/2 minus 1 plus minus root Q, each coming with multiplicity Q minus 1 over 2. So this is one property of a Paley graph. It's a strongly regular graph. Now I want to tell you a little bit about other properties of Paley graphs. Paley graphs satisfy a property known as quasi-randomness. So random graphs, that's another giant field in as a subfield of graph theory. And quasi-random graphs are graphs that are not constructed randomly, so they have a deterministic algorithm, but they behave in some ways like a random graph. Now, what that means is there are actually multiple ways of making that precise, and you can see the article that I will cite at the end of the slide by Chung, Graham, and Wilson from their 1989 Combinatorica paper. But you can think of it as like, take a property of a random graph. Let's say in a random graph where you assign edges with probability 1/2 by flipping a coin. Take a property that you think is an identifying property of a random graph. For example, you could say, what is the expected number of common neighbors of two uniformly random chosen subsets? Like that's something you can calculate using linearity of expectation and other probabilistic tools. And then you say, okay, if any other graph that is not random, but deterministic, but satisfies a similar property, then we will say that it's quasi-random. So quasi-randomness basically means it acts like a random graph through some parameters. Maybe it has the expected number of edges that you may find in a random graph, or maybe it has the expected number of common neighborhoods of two uniformly chosen subsets, as you may find in a random graph. And the intuition that is worth remembering here is the reason why Paley graphs are quasi-random is somehow tied to the notion that the squares are randomly distributed. So we know that in a finite field FQ, half the elements are squares and half the elements are not squares, right? If you look at the non-zero elements, exactly half and half is squares and the other half is non-squares. And somehow what this is getting at is that the distribution of the squares and non-squares is completely random, or it looks random to us. And this is precisely why the study of Paley graphs is interesting. Why? Well, because they're deterministic for sure. That is, once you fix a prime, then there's only one Paley graph on p vertices. There's no choice to make. But despite being deterministic, they display high degree of randomness. And at the same time, they are highly symmetric. I mean, somehow they're fulfilling so many roles all at once. They're random, they're deterministic, and yet they're highly symmetric. This is why Paley graphs are really an amazing source of graphs to study. And there's some other incredible properties of Paley graphs. I'll just mention a few of them. Paley graphs are known to be self-complementary. What that means is that if you look at the complement of the graph, then that's also isomorphic to the Paley graph. And the complement of the graph is simply the graph that you get when you erase all the edges and put edges where the edges didn't exist. It's vertex transitive. You can map one vertex to another vertex through a graph automorphism. And also they're Hamiltonian. They have Hamiltonian cycles. There's also connection to Hadamard matrices. And the Hadamard matrices are very special matrices that have entries -1, +1, and they have orthogonal columns and so on. In fact, Paley's original motivation with studying Paley graphs was in search of a construction of Hadamard matrices using quadratic residues. So really, Hadamard matrices is at the origin. It's like the origin story of Paley graphs. And Gareth-Jones wrote a very excellent article on the history of Paley graphs and Paley himself. So here are the references that I mentioned in the slide. There's the paper by Chung, Graham, and Wilson called Quasi-Random Graphs from 1989, published in Combinatorica. And then the other paper by Gareth-Jones that was recently published as a part of a conference, and it's called Paley and the Paley Graphs. You can find Jones' article available on the archive as well. Now I'm going to focus on the clique number of the Paley graph, and that's going to be the remaining theme for the rest of the talk. So consider the Paley graph of order Q. So again, all that means is that the number of elements in X is Q, Q some prime power, and the elements come from a finite field of order Q, and we connect two elements by an edge if and only if their difference is a square in the finite field. And so what we're interested in is so-called the clique number. The clique number omega x of X is measuring the size of the largest complete subgraph that's contained in X. So this is a quantity that you can investigate in any graph. It's an invariant of a graph, and we're interested in that. And this turns out to be a very hard problem in general. If you think about what the question is actually asking, it's asking something sort of seemingly basic. Because what is the clique number? After all, we want to know the largest size of number of elements in FQ such that the pairwise differences between them is perfect squares. So we're looking for a collection of elements in a finite field such that each pairwise difference is a perfect square. So it sounds like an innocent looking problem, but yet it's so out of reach. Understanding this question and determining the clique number exactly, finding a formula for the clique number is really, really hard. It's completely out of reach. And I will tell you what we know in this lecture. I will tell you the current state of art, basically. But I anticipate that this problem will take many years. I won't predict exactly how many years, but I think it will take many years to resolve this question, basically. It's too chaotic. So I'll tell you what we know. So first, I'm going to show you the following upper bound. Sorry, not lower bound. This should be upper bound. There's a typo here. So I'm going to show you the upper bound, that the clique number of the Paley graph of order Q is at most square root of Q. I'm going to show you this holds in general. And this upper bound here has a name in the literature. This is called the trivial upper bound. But it's not so trivial. It needs proof. So despite its name, it does require proof. Let me just mention that the true trivial upper bound, the one that wouldn't require any argument, is that the clique number is at most Q, right? Why? Because there are Q elements in the graph. There are Q vertices. So of course the clique number cannot exceed Q. That would be the super trivial upper bound. But the trivial upper bound says that says something a bit better. It says that the clique number cannot exceed the square root of Q. Like I said, despite its name, this requires a proof. And here is the proof. The proof is a very nice counting argument. So we start with the primitive root of FQ. So an element that generates multiplicatively all the non-zero elements of the finite field. And we're going to take a clique in the Paley graph PQ. And we're going to consider the following set. And what is the set? This is a subset of FQ, and this set is called E. And E is just all elements of the form A plus BG, where A and B are elements of the clique. All right. So this is just some subset of FQ. Now, what I'm going to show you is that this set E is not too small. In fact, I'm going to show you that this set E is quite large. It's as large as it gets. This is what I'm going to show you. This set E is very large. It's as large as it gets. So let's start with two pairs, A comma B and C comma D. And these are going to be two distinct pairs in C square. What that means is that A belongs to C, B belongs to C. So both of these are pairs of elements that come from the clique. So A is an element of the clique, B is an element of the clique. And I'm just assuming that the pairs are different. What I'm going to show you is that these corresponding numbers, A plus BG and C plus DG, must in fact be different as well. So assume to the contrary that A plus BG is equal to C plus DG, and let's see what we get. Well, if I take this equation and rearrange it, I'm going to get A minus C equals to D minus B in parentheses times G. But now, since C is a clique, we see that A minus C and D minus B must be squares in FQ, right? This is from the definition of a clique, because a clique is a subgraph of the Paley graph. That means that if I take two elements in the clique, their difference is a square, because that's why they're an edge in the graph. So this is a square and this is a square. Well, if this is a square and this is a square, then from this equation, I can conclude that G is also a square. But that's a contradiction. Well, why is that? Because G is a primitive root. G is a primitive root of FQ. So if G was a square, then because G generates all the elements multiplicatively, then all the non-zero elements in fact be a square, would have to be a square, but that's not possible. Exactly half of the elements are a square. So because only half the elements are a square, it's impossible for the primitive root to be a square. And the this is our contradiction. So that means that, in fact, A plus BG must be different from C plus DG, which means that the size of E is as large as possible. That means it has size C squared, because there's number of pairs A comma B is exactly C squared. Okay, so what do we know now? Well, we've computed this cardinality of this set, and we know that it has C square elements. But E is a subset of FQ. Because E is a subset of FQ, that means C square in particular must be at most Q, and that tells you that C is at most square root of Q. So since C was an arbitrary clique in the Paley graph order Q, well, and we've shown that C is at most root Q in size, that means that every clique has size at most root Q, which means that the clique number is at most square root of Q. And this is the proof of the trivial upper bound. And note that the trivial upper bound, in fact, can be achieved in some cases. So how is it achieved in some cases? Well, first of all, for this to be an integer, we need Q to be a square, because we're going to take the square root. And in fact, if you consider the case of the Paley graph with Q square elements, which is constructed from a finite field of order Q square, then this Paley graph has, in fact, a maximum clique of size Q. And what is that? Well, it's simply the clique obtained by taking a subfield. So FQ is a subfield of FQ square. And you can check that, in fact, this is a clique. Difference of two elements in FQ becomes a square in FQ square, which means that the clique number of FQ square is, in fact, equals to the square root of Q square. So, in fact, the clique number in this case is achieves the trivial upper bound. But I will mention that we expect this to happen just for the case when Q is a square. So in this case, we have Q square. So only for square or even powers of Q, we expect this, okay? So if you were dealing with something that wasn't a square, that didn't have a subfield like this in it, we don't expect this to hold. So this example is really an exception more than a rule. So from now on, for the most part, I'm only going to consider the case of a finite field of prime order. So I'm going to look at the case of Paley graph with P elements where P is prime, because it turns out that somehow that's even though that that's somehow like the prime case is somehow the hard case to establish. Once you understand the prime case, we have some hope for understanding the prime power case. So we're going to focus mostly on the prime case of Paley graphs of prime order, but I will mention whenever more general results pop up, I will mention the corresponding generalizations. Okay, so now let me tell you what we know about clique number of Paley graphs of prime order. So again, here we're looking at primes, and I will mention in some results general results that are true for any prime power. So what do we know about the clique number? So I already showed you the trivial upper bound. So clique number of an arbitrary Paley graph of order Q is at most square root of Q. But what about lower bounds? How do we construct cliques? That turns out to be hard. So in 1988, Stephen Cohen showed that the Paley graph of order Q has clique number that's at least a constant times log Q. This is true for any prime power Q. So in particular, it's true when Q is a prime. In 1990, there was an improvement on the result when Q is a prime P. So Graham and Ringrose showed that the least quadratic non-residue mod P is this quantity, MP, is at least as big as constant times log P times log P for infinitely many primes P. And why is this relevant? Because if NP is the least quadratic non-residue, then we can take this set 0, 1, 2 all the way until NP minus 1. And by definition of minimality, none of these elements are quadratic non-residue. That means, in fact, all of them are quadratic residues. And any difference between these two is also a quadratic residue. So what that means is that we get this lower bound for infinitely many p's. So this is not, strictly speaking, for every p, but for infinitely many p's, it's true that the clique number is at least as big as log p times log p. So which is an improvement on Cohen's result. And then there was a recent improvement after 23 years. We have Babcock, Matolsh, and Rusha. They proved that you can actually improve the trivial upper bound. So the trivial upper bound I already proved to you in the previous slide, which says that the clique number of Paley graph of order p is at most square root of p. So, well, even improving that by 1 took a significant amount of effort, and they were able to establish that. And they established it for 3/4 of the primes of the form p equals to 4q plus 1. So they didn't do it for every prime, but they showed it that roughly for 3/4 of the primes, 1 mod 4, this is the case. And then there was the recent breakthrough by Hanson and Petridis. And Hanson and Petridis showed that the Paley graph of order p, if p is prime, is in fact has a clique number that is less than or equal to a square root of p over 2. I think there's also a plus 1 here. So square root of p over 2 plus 1. Now, this thing is a significant improvement in the trivial upper bound because the trivial upper bound only gave us root p, and this is a multiplicative improvement in the coefficient. And they did this for the case when you have a Paley graph of prime order. But now you might ask, well, what about other Paley graphs? Now, you can't prove this for all Paley graphs because it's just not true, as we saw in the previous example, that the trivial upper bound actually does hold in some cases. Especially it holds when you're looking at the case when you have a finite field of square order. So somehow, if you want to improve, if you want to generalize Hanson and Petridis result, you have to be careful because you can't just blindly replace p with q because q could be a square, in which case this is not true. But you can replace instead p with odd powers of primes. And in fact, Chi-Ho Yip, he generalized the Hanson-Petridis result to Paley graph of order arbitrary odd power prime. So he showed an analogous result to this in the case of odd power of prime. And just recently, this year, Chi-Ho also extended his results to generalized Paley graphs and other cyclotonic graphs. And this is kind of a big result because Paley graphs just happens to be only one graph among a whole family of graphs. So generalized Paley graphs in particular is the one where instead of requiring x minus 1 to be a square in a field, we say that it's a dth power in a field. So dth power could be cubic, it could be a perfect cube, it could be a perfect fourth power, and so on and so forth. So the Paley graph is a very special case when you require the difference between two elements to be a perfect square. So that's the d equals to 2 case. But in general, d could be anything, and dth power Paley graph is known as a generalized Paley graph. And there, you know, you can expect to get square root of p over d here instead of p over 2, square root of p over d. And basically, that's what Chi-Ho Yip proved just this year. So this is kind of a breakthrough result I wanted to mention. And I also wanted to mention what we expect the clique number to be. So by numerical computation, it's been observed that the clique number of Paley graph of prime order is less than any positive power of p, constant depending on epsilon. So it's less than p to the epsilon for any epsilon, constant being implicitly depending on epsilon. And from this, we expect that the clique number is small. So clique number of a Paley graph of order p is expected to be closer to the lower bounds that was obtained as opposed to the upper bounds, right? Because the upper bounds is like things like the square root bound or Hanson Petridis bound. These are like square root of P. But in reality, it seems like the clique number is tiny. In fact, it seems that the correct order of the clique number of Paley graph of prime order is in fact polylogarithmic in P. And what that means is that it's a polynomial function in log P. So it's extremely tiny. And in particular, I've seen at least one paper predict that some constant times log P squared could be a good candidate for the clique number of a Paley graph of prime order. So these are the kind of the state of the art for the clique number of Paley graphs and related graphs. And now I wanted to talk about a few other topics that are closely related to Paley graphs. And the reason I'm talking about this is that this is also the way Hanson and Petridis motivate the result. And the whole point of the lecture series is to introduce the audience to Paley graph and introduce the audience to these amazing results. But I also wanted to give a proof of the Hanson-Petridis theorem in this lecture series. Now, today's lecture, I'm just going to introduce what they proved, but I'm not going to show you the proof they had. The proof they had in their paper uses what's called Stepanov's method. And that's a very intricate idea that uses what's called an auxiliary polynomial. And it looks at things like constructing a polynomial with various conditions and looks at the order of vanishing at a bunch of points. And it's a bit hard for me to motivate why that works. It really feels like magic, but it's a systematic method. But I want to give another proof of this result that was devised by Di Benedetto, Salimoji, and White. And that will come up in the third lecture. But today, at least, I wanted to give the motivation that Hanson and Petridis have in their paper. So clique number of a Paley graph is connected to concept of additive decomposition of a multiplicative subgroup of a finite field. Now, let me motivate these ideas. So we're going to start with very general remarks. So suppose F is an arbitrary field. At this point, F could be any field. And in fact, I'm going to show you an example that involves complex numbers. And if D is an integer at least 2, then ZD is going to denote the solutions to the equation Z to the D equals to 1. So this is just elements which are Dth root of unity in the field. So if the field F is the field of complex numbers, then we're familiar with the set ZD. ZD consists of a bunch of points on the unit circle. In particular, it's of the form, it consists of all elements of the form e to the power of 2 pi I k over d, where I is the imaginary number and k is an integer between 0 and d minus 1 inclusive. And here's the main intuition to keep in mind. By definition, ZD carries a multiplicative structure because it's a solution to a multiplicative equation. In other words, if you take 2 elements in ZD, you can multiply them, you're still going to end up in ZD. So it's a multiplicative object. So because of that, this is a general principle that we expect that ZD does not have rich additive structure. In other words, if you take 2 elements in ZD and add them, you shouldn't, that should be not really, there should be no structure to that. And there should just not be much additive structure inside ZD. So additive structure, what does that mean? Let's make it precise. Well, additive structure means that it can be realized as a sum set of 2 subsets. So one way to show that ZD does not have rich additive structure is to show that you cannot express ZD as a sum of 2 sets, A and B, of course, with the condition that A and B are non-trivial. So there are not singleton sets. And just to remind us of this notation, A plus B is the sum set notation, and that stands for all elements of the form A plus B, where A is in A and B is in B. So we don't expect this kind of relation to hold, because if this relation held, that would mean that ZD simultaneously achieves a multiplicative structure and additive structure, which is extremely unlikely. So here's a nice result that is mentioned in the introduction of the paper, Refined Estimates Concerning Sum Sets Contained in the Roots of Unity. That's the title of their paper, by Hanson and Petridis. And here's the result. I'm calling this a tricky exercise from complex analysis, because it's something that you can present to students learning complex analysis, but it is kind of tricky if you haven't seen it before. And the result says the following. It's a very elegant statement. Suppose that D is bigger than 4. So remember, D here is the exponent that appears here. So ZD is these roots of unity. So that means we're looking at the case when D is bigger than 4. So any dth root of unity, so there's D of them here, and we're saying that there's no way you can write it as A plus B. You just cannot express it as a sum of two sets. And this result is, at this point, is only about complex numbers. So how does the proof work? So assume that B is at least A, which is at least 2. So without loss of generality, let's assume that B is the bigger set. And because I'm assuming to the contrary that, because I'm assuming that it's a non-trivial, it means that B and A must be non-singletons. So they have size at least 2, and I could assume that B is the bigger set. Now I'm going to take two elements, A1 and A2, in A. Then I'm going to observe that ZD, which is the dth roots of unity, is a subset of S1, which is the unit circle in the complex plane. Now, because of that, it follows that A1 plus B and A2 plus B are both subsets of S1. This should be S1, 1 in the superscript. So why is that? Because I'm assuming that ZD is A plus B and ZD is contained in S1. That means A plus B is contained in S1. In particular, A1 plus B and A2 plus B are subsets of the unit circle. But if that's the case, then I can consider the difference between A1 and A2. And what do I get? A1 minus A2 is A1 plus B minus A2 plus B. And this B here can be an arbitrary element of the capital B, which means that this object has at least B representations as difference in S1 minus S1. So just to recap, I started with two elements of the set A, and I looked at their difference. And I just showed you that that difference, A1 minus A2, can be represented in B different ways, cardinality of B different ways, as a difference in the unit circle. So this is very important, that A1 plus B and A2 plus B are both elements of the unit circle. But it's a fact, and very straightforward to show, that any non-zero complex number is a difference of 2 points in the unit circle in at most two different ways. So if you have any complex number whatsoever, and you want to write that as a difference of 2 points on the unit circle, you can do it in at most two different ways. This kind of follows from the geometry of the unit circle. Well, first of all, if I have a very large vector, there's no way I can even write it as a difference of two elements in the unit square, just because of the triangle inequality. If you take difference of two elements in the unit square, well, in modulus, the difference is at most 2, right? But if you can write it as a difference of two elements in the unit circle, then there's really only two ways to do it, at most two ways to do it. You can just think of the way subtraction of vectors work, and you must be inside the unit circle. So you can see that if I have a given vector in this direction, there's really two ways you can do it. There's only like two ways you can express this. So how is it possible? I just told you here that you can represent it in at least B ways as a difference of two vectors in the unit circle. But here I'm saying that any non-zero complex number is a difference of 2 points in the unit circle in at most two ways. In at most two ways. Well, the only way not to get a contradiction is that B must be 2, because otherwise we have a contradiction. But if B is 2, then because of this inequality, A is sandwiched between 2 and B, so A is also 2. But if A is 2 and B is 2, then ZD is too small. How could you have sets of size 2 and size 2 adding together? Then we can conclude that D must in fact be 4, which is contradiction because I'm assuming D is at least 4. D is bigger than 4. So this is the proof of this very nice result that kind of follows from the geometry of the complex plane. Okay. Now, what happens when D is at most 4? So this result was about D bigger than 4. And what happens, we're dealing with a complex plane and D is at most 4. Well, when D is less than 4, then there's no way it can admit an additive decomposition, because if D is strictly less than 4, then ZD is too small. It's just too small. But amazingly, when D is 4, so that means you're looking at the 4th root of unity in the complex plane. Well, there's only 4 elements. It's plus minus 1 and plus minus I. Actually, you can represent it. You can represent it as a sum. So it has a non-trivial additive decomposition. But this is just one case. It's kind of like it's too small to be concerning to us. At the small scale, when you're looking at small sets, some sort of coincidences like this will happen, but this is not the kind of phenomena we expect to hold in general. I mean, we just showed it's not possible for D bigger than 4, but this is still kind of a neat observation about 4th root of unity. Okay, but here's our question. What happens when we replace complex numbers with an arbitrary field, a finite field, Fp for a prime P? And so that's the question we wanna ask. Now, the argument that we just discussed doesn't work because the unit circle geometry is lost. There's no such thing as unit circle in a meaningful geometric sense, because the group of this group ZD is just a subset of a line, right? So Fp is just a line. There's no intuition from unit circle geometry here. Now, it's worth mentioning that if you look at the entire group of units, so that is a special case when D is P minus 1. When D is P minus 1, then you get everything. You get every non-zero element just because every element to the power of P minus 1 is 1. Every non-zero element raised to P minus 1 is 1 in a finite field of order P. So in fact, this is a very special case. This is like an edge case. And this one, interestingly, does have a non-trivial additive decomposition. And that's because you can look at the elements 1 up to P minus 1. And this set can be expressed as a sum set of a set with 2 elements and a set with P minus 1 over 2 elements. And it's kind of clear how you do it, because if you pick 0 from here and you add 0 to any of these, you're going to get the first half of the elements mod P. And if you pick the second element, P minus 1 over 2, and you add it to all the other elements in the second set, you're going to get the second half of the elements mod P. So this is why this exists. But again, this is an exceptional thing because this is like the extreme case when D is as big as possible. But we believe that no such example exists. No such example like this exists when we're looking at ZD, where D is a proper divisor bigger than 4 and less than P minus 1. So we're going to talk a little bit about this. And there's a particular case when the value of D is exactly P minus 1 over 2. So why is this relevant? Why is it connected to Paley graphs? Well, when D is equal to P minus 1 over 2, then what is the set Z sub D? By definition, it's all the elements, all the non-zero elements in the finite field, such that when you raise Z to P minus 1 over 2's power, you get 1. But by definition, solution to this equation is exactly all squares in FP star. So that's why this set here is relevant to us, because it's the set of quadratic residues in FP star. Now, how do we show, or how do we attack, how do we approach showing that an object like this is not expressible as a sum set of two non-singleton sets, A and B? So one classical approach for understanding these sum set decompositions is to consider so-called character sums. And the character sums are defined as follows. So we're going to have chi, and that's going to be a homomorphism, a multiplicative homomorphism from FP star to C. So this is going to be fixed. And the character sum S chi AB is defined to be a double sum, where I'm summing all the elements of the form chi of A plus B, where A ranges in capital A and B ranges in capital B. So this is a double sum that goes through every pair A comma B exactly once and computes the value of the character at A plus B. Now, we may often extend the domain of the character. So we might want to start at FP. The only difference between FP and FP star is that FP has 0 in it. So, but that's easy to deal with. We can just declare chi of 0 to be 0 if you wanted the map to start at FP. So we call chi a multiplicative character of a finite field. So here's a result by Vinogradov, a classical result that shows that the character sums are bounded in the following way. So if I have two subsets of FP, and chi is a non-trivial multiplicative character, then it turns out that this double character sum is in fact in absolute value at most square root of P times the size of A times the size of B. So let us see, when is this result useful? Well, if you look at the definition of S chi, it's got this A times B many terms, the size of A times size of B many terms, and you're adding up a bunch of character values. But it's known, just basic fact about characters, that each value chi A plus B, which in general is a complex number, has modulus at most 1. So when we add up the values in that sum, we have at most, so we know that, the value of chi of A plus B is exactly 1. If A plus B is not 0, then the value of the character is exactly 1. This is basic group theory. So in any case, the value of chi of A plus B in absolute values is at most 1. And there's exactly A times B many terms. So we get this for free. Now, because we get this for free, how is Vinogradov's lemma useful? Well, it's only useful if the upper bound that's furnished from Vinogradov's result is smaller than the result that we get for the trivial upper bound. And that will happen exactly when this inequality is satisfied. And if this inequality is satisfied, then we know that Vinogradov's theorem gives a non-trivial upper bound on the character sum. And this happens exactly when the size of A times the size of B is bigger than P. So under this range, we have a nice non-trivial character sum estimate due to Vinogradov. And here is a conjecture in the field. As far as I know, it's widely open. And the conjecture says that, in fact, the character sums are always kind of, there's always cancellation in the character sums. So if there was no cancellations, you would expect to get A times B. But this is saying that you have strictly less than A times B for the size of the character sum. And what is the hypothesis? Well, epsilon is fixed from the beginning, and this should be true for a non-trivial character chi. And for any prime P that's sufficiently large, how large? Well, that's going to be determined by epsilon. And then the other condition is that this should be true for all sets A and B, which has size p to the epsilon. Obviously, epsilon has to come into play somehow, and it comes into play with this condition. So we're not claiming that this is true for all A and B. We're only claiming that it's true when A and B have size that's bounded below by p to the epsilon. So this is a conjecture, and yeah, so figuring this out and resolving this conjecture would shed light on many of the problems on additive decompositions over finite fields. So let's think about what Vinogradov's theorem tells us. So if you have two sets that are subsets of FP such that A plus B is contained in Z sub D for some proper divisor, D of P minus 1, let's say that's the case. This means that I'm assuming that I'm assuming that ZD admits an additive structure inside. So even though ZD is not equal to A plus B, the fact that A plus B is a subset of ZD already indicates that ZD, I'm assuming that Z sub D contains some additive structure. And we want to say that this kind of thing is rare to happen. So what can we say? Well, let chi be a multiplicative character of the order P minus 1 over D. Then it's clear that chi of Z is 1 for each Z in ZD. Then what happens if I calculate the double character sum? Well, I'm going to get this double sum. And because A plus B is in ZD, and the value of the character sum at A plus B must be 1, because the value of the character on ZD is always 1. So here I'm using the fact that A plus B is inside ZD to get that each of these terms is 1. And how many terms are there? Well, there's exactly cardinality of A times cardinality of B terms out there. But if size of A times size of B is bigger than P, then according to Vinogradov's theorem, we have a non-trivial upper bound on the character sum, right? Then this is less than A times B. But that's a contradiction because just above, we show that S chi of AB is exactly A times B. This means that we've obtained the following corollary. We have obtained that if A plus B is inside ZD, where D divides P minus 1, and D is proper divisor of P minus 1, then the only way we don't get a contradiction is that A times B in size is at most P, right? This is forced because if A times B is bigger than P, then Vinogradov's theorem leads to a contradiction. That means the only way to avoid contradiction in this case is to force A times B to be less than P. So this is a corollary of Vinogradov's theorem. And the way we think about this is that it shows that for an additive decomposition to happen, it means that P has to be large, quite large compared to size of A and B multiplied together. And what did Hanson and Petridis do? And this is their main theorem. I think writing it in this way hopefully will motivate what they proved and what they proved, how does it strengthen the known results? So if you look at this corollary is what we get from Vinogradov's theorem, right? This is all we can say. But what did Hanson and Petridis prove? They proved something much stronger. And here's what they showed. If you have a prime number and such that A and B are subsets of FP, such that A plus B is inside ZD union 0. So it's not exactly this. It's just tiny bit different where you allow 0, but it's close enough. What they showed is that not only A times B is less than or equal to P, they showed that A times B is less than or equal to D plus the cardinality of B intersect minus A. So minus A is just you take the elements of the set A and you put a minus sign. And we're looking at an intersection of B with minus A. This is just sort of the additional term you add, but the first term here is D. Now, it's not P, it's D. So for example, if D is P minus 1 over 2, that's already P minus 1 over 2 is much better than P here, right? So this is a kind of cool result. Let me say a few words about the corollary of their work. So suppose P is a prime number, and suppose that A and B are, they satisfy, this should be A plus B. So A plus B is a subset of ZD, and D properly divides P minus 1. So I'm just in the same situation as before. So I'm looking at this. This is the condition that I'm looking at. ZD, which is the group of Dth roots of unity, it contains a non-trivial additive decomposition inside it for some proper divisor of P minus 1. So they showed that in that case, the size of A times B is D. And in fact, all sums, A plus B, are distinct. This is the corollary of the previous result. Now, what does this mean? In particular, if D is a prime number and A is at least 2 and B is at least 2, then there's no such decomposition. Why? Well, if D is prime, how is it possible to have A times B equals to D? And if D is prime, the only way that's possible is either A is 1 or B is 1. So there's no way that you can have a non-trivial additive decomposition in the case when D is prime. Now, in the case that was of interest to us, the case of quadratic residues, that's the case when D is P minus 1 over 2, right? That's because ZD, in that case, Z sub P minus 1 over 2 is a set of quadratic residues in FP. And if P minus 1 over 2 is itself a prime, then it's impossible to have an additive decomposition. According to Hanson and Petridis result just above, if this value of D, in this case, P minus 1 over 2 is a prime, then you cannot express Z of P minus 1 over 2 as a sum of two subsets. And in other words, for these primes P, there is no non-trivial additive decomposition of a set, Z sub P minus 1 over 2. And so here's a natural question. Can we even find infinitely many primes P such that P minus 1 over 2 is also prime? Because if you can show that there are a lot of primes like this, then you can apply Hanson-Petridis result directly, right? So for those primes for which P is prime and P minus 1 over 2 is prime, then Hanson-Petridis result goes through directly, and it shows that Z sub P minus 1 over 2, the set of all quadratic residues, does not admit a non-trivial additive decomposition. So we should interpret that result that by saying that quadratic residues do not have additive structure. And anyways, this is related to what's called Sophie-Germain primes. So Sophie-Germain studied these primes in relation to Fermat's last theorem. And these are the primes P such that 2P plus 1 is also prime. And these primes are obviously connected to primes of this kind. And as far as I know, this is an open question. So let me mention Sarkozy's conjecture. So Sarkozy conjectured that for any prime P bigger than 3, there's no non-trivial additive decomposition of the set of quadratic residues. So the Hanson-Petridis proved it in the case when P minus 1 over 2 is prime, but in general, there's no reason for P minus 1 over 2 to be prime. In fact, P minus 1 over 2 is usually not prime. So this is kind of the wide conjecture. This is one of the kind of intensely studied open question in the recent decade in the field of additive combinatorics. And it's such an appealing statement. All it says is that you look at the quadratic residues in FP star, and these are exactly the squares in the field, and there's exactly half of them, so P minus 1 over 2 elements. And it just says that you can't express that as a sum set in a non-trivial way. A plus B, you cannot write it in the form A plus B, where both A and B have size bigger than 1. And there's a very interesting observation that George Sheikan made in Hanson-Petridis' paper. So Hanson and Petridis posted their preprint, and after that, Sheikan observed something amazing that he could deduce from their result. And Hanson and Petridis included Sheikan's result in their latest version of their paper, and in fact, it appears in Hanson and Petridis' introduction. And they of course credit Chacun for this observation. And what George Chacun showed is that Sarkozy's conjecture, in fact, is true asymptotically in the following sense: that if you look at the number of primes for which Sarkozy's conjecture fails, so f of x is the number of primes for which you can express the set of quadratic residues as a non-trivial additive decomposition, then in fact there can't be that many primes. So the set of primes f of x with this condition, so the set of bad primes, satisfies the condition that the limit of f of x divided by pi of x as x goes to infinity is 0, where, as usual, pi of x is the prime counting function. It's the number of primes up to x. So in other words, this result shows that Sarkozy's conjecture holds for almost all primes, which is already, in my opinion, a big breakthrough in the field. And the proof of this result uses the ideas that are both in the Hanson and Petridis result, but also a very foundational and important work by Kevin Ford on the prime divisors of a given number. So this paper is all about when can you say a certain divisors of a given number is contained in a certain interval. So it's obviously, as you can see, it's been published in Annals of Math, so it's a very important work. And now I wanted to mention a few more things, just two or three more slides, and I'll be done. There is also an interesting, exciting development in the version of Sarkozy's conjecture known as restricted version of Sarkozy's conjecture. So Sarkozy's conjecture says that you cannot write the set of quadratic residues as A plus B, where A and B are non-trivial subsets. They're non-singleton subsets. But what if I ask, instead of A plus B, I ask, can I write it as A sum A, and here I have the symbol plus sign with a hat on it, this restricted sum symbol. And what that is that I'm adding A and A prime, where A and A prime are different elements of the same set A. And so Ilya Shkredov showed in 2013, about 10 years ago, that if P is bigger than 13, if prime is bigger than 13, then the set of quadratic residues cannot be expressed as a restricted sum for any set. So this is an amazing result because this kind of there's no restriction on the prime. So in Chacun's result, this was asymptotically true. Of course, Sarkozy's conjecture is different because there's A plus B. There are two sets. Here, there's only one set, but this is a restricted sum. But it's kind of cool, amazing that this result is true for any prime, P bigger than 13. And there are some examples of what happens when P is less than or equal to 13. And you can find some small counterexamples. It's not so interesting. I think this is already cool. And I wanted to mention a very recent result. Just a month ago, Chiho Yip generalized Shkredov's result to finite fields of prime power cardinality. So Shkredov's result is about the case when P is prime, and Chiho Yip proved exactly the same result when P is replaced by a prime power. So P is Q is a prime power, and Q is bigger than 13. Again, he showed that the set of quadratic residues cannot be expressed as a restricted sum, as a restricted sum set. And here the papers, Shkredov's result was published in Arte Arithmetica about 10 years ago. Obviously, Chiho Yip's paper is not published yet because it was just posted a month ago. But you can find it in the archive under the name Restricted Sum Sets in Multiplicative Subgroups. And here's the archive code, 2309.10950, if you want to have a look. And this is the last slide. So let me just return to the discussion of the Hanson and Petridis result, A plus B. So suppose that ZD, so this is the dth roots of unity together with 0, I suppose that it has some additive decomposition. for some d properly dividing p minus 1, then according to their result, all non-zero sums a plus b must be distinct. And now we can just use b equals to minus a, and we're going to get the following result. We're going to get that if p is prime and if d is a proper divisor of p minus 1, if you take a subset of fp such that a minus a is inside ZD union 0, what that means is that A is a clique in the Paley graph or in a generalized Paley graph. And then you see that A times A minus 1 is at most D. And from that, we get the following corollary. If P is 1 mod 4 and A is a clique in the Paley graph of order P, then we know that A minus A is inside ZD with D equals to P minus 1 over 2. That means that size of A times A minus 1 is at most P minus 1 over 2. And this is a quadratic inequality. You can solve for A from here and see that A must be at most square root of 2P minus 1 plus 1 over 2, which means that the clique number of the Paley graph is at most square root of P over 2 plus 1. This is just basic algebra from there. And the last thing I want to mention is that this inequality here, right here, this actually just exactly follows from this inequality if you set B to equal to minus A. Why is that? If you set B to equal to minus A, then this is going to give you A times A. So size of A times size of A. But this is going to be just size of A, because when you intersect it, you get one element. So this is size of A square minus the size of A must be at most to D. But that's exactly what I wrote here. Size of A square minus the size of A is at most D. And we've shown that any clique in the Paley graph must satisfy this inequality, which shows that the clique number of the Paley graph is at most root P over 2. And again, I didn't show you how Hanson and Petridis did it, but I will show you a different proof in the third lecture of this mini lecture series. And that's all I have for today. So thank you for your attention.
Thank you, Shamil, very much for this talk here. Yeah, thank you very much. Are there any questions to Shamil? So I just have two very simple questions. The first one is about this Hanson Petridis upper bound. So is it the best known upper bound currently?
Yeah, I believe that it is, in fact, the square root of P over 2 plus 1 is in fact the best known upper bound. And I mean, I could be wrong. So this is the best known general upper bound, right? For a particular P, yeah, we can, of course, calculate. And in fact, there are tables. People have calculated the clique number up to like primes up to 10,000, something like that. So I think maybe up to 10,000 for P up to 10,000 they've calculated. And of course, the result is always much less than much less than this. Yeah, because usually it's polylogarithmic. So in fact, based on the data that they have up to 10,000, they think that the clique number should be log P square. That's tiny. So I see there's a comment in the chat by Chiho.
Oh, you're right. Yeah.
So I'm just gonna read his comment so people can hear maybe in the video. Yeah. So the comment says, just a minor remark. Sarkozy himself only conjectured that there's no additive decomposition when P is sufficiently large, although probably the conjecture is true for all primes P bigger than 3. No counterexample has been found as far as I know. Okay, that's really cool. So what Chiho is saying is that here I talked about Shkredov's result, and that was the case when P was bigger than 13. But that's for the restricted subset. And there's counterexamples when P is less than 13 for restricted subset. But for Sarkozy's conjecture, he's saying that we don't have anything, no counterexamples as far as we know. But the conjecture itself is only made in its original form for sufficiently large p. So if you find some counterexample for small p, it's not the end of the story, I guess. That's the point. There might be hope to prove it for sufficiently large p. But thank you for the comment.
Okay, any other questions? Comments? Well, as for Sophie domain primes, are there any results about this? Because it is so beautiful conjecture. Yeah, it is easy to explain here, just one line and no results, I think.
Yeah, I believe we don't know anything of the kind where we can show primes p such that AP plus B is also a prime for infinitely many primes. We don't have any results of that kind. And you probably noticed already, but we also don't have any results of the kind, like there are infinitely many primes of the form n squared plus 1. Like there's infinitely many primes of the form some polynomial. Basically, every time you want to show existence of a prime of particular kind, we don't have anything except Dirichlet's theorem and arithmetic progressions. That's really the only thing we have. But in that case, it's an plus b, but n doesn't have to be prime, right? It's just an plus b. But if you ask, I guess a generalized Sophie-Germain primes would be if you ask primes of the form AP plus b, where p is prime and AP plus b is prime. Then you're asking kind of two things at once. And as far as I know, we don't know. So I think somebody also I recently saw a discussion where people were saying, well, what about primes p such that 2p minus 1 is prime? Instead of 2p plus 1. And so those ones don't have names, but they're just equally as open. We expect that there are infinitely many of them, but we can't prove it. Yeah. And somebody who's more knowledgeable about analytic number theory can correct me. Maybe Kyle knows about this, but we might have some heuristics on the number of Sophie-Germain primes up to x. So some probabilistic models that tells us that, well, we don't know there are infinitely many Sophie-Germain primes, but we expect that up to x, we have like log p many Sophie-Germain primes, or like log x many Sophie-Germain primes. So I expect that some analytic number theorists may have heuristics that predict, but not prove the existence of infinitely many Germain primes.
I see. Okay, thank you.
Yeah.
Any other questions? Okay, if not, then let us thank our lecturer. Again, thank you very much. It was really very interesting. Even with regular definition, you can explain everything. It's so nice. Thank you so much. Yeah. Okay, so in 2 weeks, there will be one more lecture given by Shamil, and it will be introduction to the theory of directions. As for me, it will be something very new. So I have no idea what does it mean. So I'm looking forward very much to seeing you again in 2 weeks. Okay, thank you very much. Yeah, okay, see you. Bye.
Yeah.
Bye. Bye.
So if you just didn't go for a second, I did want to share something.
Yeah, sure. Sure.
It's this Wikipedia link. You can have a look.
Yeah.
It's called a Cunningham chain. And what this is a generalization of Sophie-Germain primes.
Oh, I see.
And instead of asking for 2p, you want 2p plus 1, 4p plus 3.
Yeah, right. Yeah, right.
So this is also interesting.
Yeah.
Okay. Anyways, thank you for the invite, Elena, and I'll see you in 2 weeks. All right.
Yeah, see you in 2 weeks. Yes, thank you. See you. Bye. Yeah, bye. Have a nice day. Yeah, okay.